Good morning from Vancouver. My name is Michael Monagan. The title of my talk is Sparse Polynomial Interpolation and Computing Roots of Polynomials over Finite Fields. The application is sparse polynomial interpolation, but the focus of the talk is on the computation of roots of polynomials over finite fields. Let me introduce the problem. The input is a polynomial f over a finite field fp. Here p is prime, and the polynomial has degree d. And in our application, we know from the application that the polynomial has d roots in the finite field. Fp is the integers mod p. So we know that the polynomial splits over the field, and the output is going to be the roots. And I have an example in Maple for this prime p here. The factor command, mod p, factors a polynomial over a finite field, over the field mod p, and the polynomial is x to the fourth plus 1. And in this example, you can see that there are 4 factors, so there's 4 roots. I implemented the factorization command a long time ago. I also implemented a specialized command, roots, that just computes the roots of the polynomial. And the format for the roots is the root, and the 1 there is the multiplicity of the root. Question: what is Maple doing? What algorithm did I implement? Let me speak to that now. So let's suppose the polynomial has roots alpha I. So the alpha I are elements of the finite field. And I'm going to assume that the prime is much bigger than the degree of the polynomial, because otherwise, if the prime is the size of the polynomial, all you need to do is to try all possible values for the field. You can try x equals 0, x equals 1 to see if it's a root, x equals 2, x equals 3, and so on up to p minus 1. So you could find the roots by exhaustive evaluation. So the problem is to compute the roots of the polynomial. The code that I implemented is the Cantor-Zassenhaus algorithm from 1981. So CZ stands for Cantor-Zassenhaus, David Cantor and Hans Zassenhaus. And as far as I know, all computer algebra systems are using this algorithm. And I implemented it in 1992 in Maple. There is a more recent algorithm. It's called the tangent graph algorithm. The authors of the algorithm are Grenet, Van der Hoeven, and Le Cerf. And it does have a restriction on the prime. The prime has to be a Fourier prime, a prime of the form some integer times 2 to the k plus 1, where that integer sigma is not too big. And I have an example of such a prime. And so to use this algorithm, you need that the prime has this form. In the sparse interpolation problem, you are free to choose the prime, so we can choose it to be of this form. Now, before I present some theoretical results, let me mention the multi-point evaluation algorithm. Let's suppose we have d points in the field, and we simply want to evaluate the polynomial at the points. That's called the multi-point evaluation problem. If we're computing the roots of a polynomial and we want to check that they are actually roots, then we would want to evaluate at the roots to make sure we get zeros. So down below, I have complexity estimates for the 3 algorithms. This is the standard fast method for evaluating a polynomial. And they are expressed in terms of m of d. So what's m of d? M of d is the cost of multiplying 2 polynomials of at most degree d. So the cost of evaluating a polynomial at d points is of order m of d log d. Basically, you have to do the equivalent of log d multiplications. The cost of computing the roots with this Cantor-Zassenhaus algorithm is order m of d log d times log p. So there's an extra log factor there. And the cost of computing the roots with the new tangent graph algorithm is ordered m of d log p. And you'll notice that it's a factor of log d better. So tangent graph is order log d times faster than Cantor-Zassenhaus. But log d is not very big. If d is 1 million, log base 2 of d is 20. It could depend on the constants in the algorithms as to whether tangent graph is really faster or not. So there's a question, is the tangent graph method actually faster? And I have here, I've done a C implementation of the tangent graph method, and I'm going to compare it with Maple and Magma's implementation of the Cantor-Zassenhaus algorithm. So my C code is using FFT-based algorithms for the multiplication for the M of D. And I'm going to compare it with Maple and Magma. As stated here, Maple and Magma are both using the Cantor-Zassenhaus algorithm, but Maple's multiplication algorithm is quadratic, at least some of the sub-algorithms. The division algorithm is quadratic, whereas Magma's multiplication algorithm is using an FFT, and it has this complexity in general. And what you can see from this little table of timings, I've tried it for different degrees. So I have the input is a polynomial of degree d with d roots, and in the prime, the field is this one, and we're going to just time Maple, Magma, and my C code. And for d equals 100, you can see Maple is 0.15 seconds. There's something wrong with Magma's clock here. It really is a lot faster than that. I think it's closer to 0.15 seconds like Maple. The C code, the time does not register yet. At 1,000, degree 1,000, Maple and Magma are both taking about 2 seconds, and the C code is 0.01. At 10,000, you can see that Magma's fast method, it's fast FFT based arithmetic, polynomial arithmetic, is starting to gain on Maple, and that there's a further gain the further we go down the table. But over here on the right, you can see that the tangent graph method really is a lot faster than the Cantor-Zassenhaus algorithm. So I have a C code for implementing the tangent graph method. Question, how can I integrate the C code into Maple? I'd like to be able to use it in Maple. And what I have implemented is I've used I guess it's called the Maple foreign function interface, so that I can call some C code. And the way that works is as follows. In my C code, I have a subroutine called roots64s, which computes the roots. The input is the array A of coefficients of the polynomial. That's the coefficients of f of x. The degree of f of x, another array for storing the roots, that's the output array, and the prime. And here, long is shorthand for long int. This is a 64-bit signed integer. So the code supports primes up to size 63 bits. The way to link this C code up to Maple is to create a shared library, which is done with this command using GCC. It creates this shared library. And then within Maple, the way to access my C function, roots64s, from that C library is as follows. I define an external routine. This is the name of the routine in the C library. I have to tell Maple what the inputs are, and this is how I'm telling Maple that the input is an array of coefficients. This is for the degree, an array for the roots, the prime, the name of the library, and the routine returns the number of roots found. And here's a little example. I've input a prime, and down here I've input the polynomial. This is the polynomial x to the 4th plus 1. And I've created an array for the output roots. I've executed it from Maple. It returns it found 4 roots, and the roots are down the bottom, and then they have the same roots that I showed previously. So this is a way to get Maple to be able to call the C code. I found it actually quite straightforward to do this. Now, what I'd like to do for the rest of the talk is just explain the method, the graph, the tangent graph transform. There's one main idea and 2 additional ideas. So I'm going to switch from using f of x to p of z because my co-author used p of z. So the polynomial, p of z, is the polynomial I want to find the roots of. It's over a finite field and it has degree d. The Graef transform of a polynomial is the polynomial, so I'm denoting it g of p, it's the polynomial times the polynomial at negative the variable. That will give a polynomial of twice the degree, but the powers will be even powers in z. So I'm going to replace z by the square root of z to reduce the degree back down to d. So that's the definition for the Graef transform. But the following lemma tells it what it actually means, what it does. If my p of z polynomial has roots alpha I, the Graef transform squares the roots. It squares the roots. That's what it does. Now, the main idea of the method is the following. If I have a prime of this form, I'm going to pick a power of 2 and choose s, which is p minus 1 over that power of 2, to be in this range. I'll be able to do that if sigma is small and k is large. I'll explain why this range later. So let's suppose we do that. We pick a value of s. That defines n, and we're going to apply the Graef transform n times. We're going to compose it n times. So we're going to square the roots n times. This means that the transform polynomial will have roots alpha I to the r. Observe the following. We chose s to be p minus 1 over r. From that, you can see that p minus 1 equals r times s. And from that, alpha I to the s is alpha I to the p minus 1, which is 1 by Fermat's little theorem. So what this means is that alpha I to the r, the transform roots, are s roots of unity. And the idea is to compute not alpha I, but the rth powers of alpha I using brute force. And the way to do that is to pick an element from the field of order s. We go through all the values, all the powers of omega I, omega to the I. We evaluate our transform polynomial at those powers, and we just see which ones are 0. This should say such that p of omega to the I is 0 for 0 is less than or equal to I is less than or equal to s. And that will give us the set of alpha i's to the r. And the way we're going to do that is, well, this is a multi-point evaluation problem. We know how to do that. So in this way, I get the rth powers of the roots of my polynomial. Question, how do I get the roots of the polynomial from the rth powers? That's the second idea. That's why the algorithm is called the tangent Graef transform. You'll see the tangent coming in a moment. So consider the following polynomial. Let p tilde of z be p of z plus epsilon, where epsilon is a symbol, mod epsilon squared. So this is like a perturbed polynomial. The lemma says that the transformed polynomial can be expressed as the original polynomial plus the derivative times epsilon. You can see that this is just coming from Taylor's theorem. What happens when we compute the Graef transform g of the perturbed polynomial, p tilde of z? What we get is p of z times p of minus z. That's the Graef transform of p of z plus some polynomial in epsilon here. And if you look closely, you'll see that there's 3 polynomial multiplications there. So we can compute this Graef transform of the perturbed polynomial using 3 multiplications. And then what happens if we compose it n times? We're going to end up with an expression of the form a of z plus b of z times epsilon. And it turns out that a of z is just the Graef transform composed n times with p. We can do that then in 3 times n polynomial multiplication. So it's straightforward to compute it. The lemma 3 tells us how to use that. If we consider the a of z polynomial and suppose we have a root of it, if it's not a multiple root, then we can get the root that we're looking for using this formula. Alpha is a root of the original polynomial. So this is going to allow me to go and get alpha I from alpha I to the r So in summary, what the method has to do, it has to compute the Graef transform composed n times of the perturbed polynomial. That takes 3n multiplications. And then we have to evaluate the A polynomial, its derivative, and the B polynomial in order to apply this formula. And we have to do that at powers of omega. Omega is an S root of unity, and that's a multi-point evaluation problem. So that's the algorithm. Question, what's actually happening to the roots under the transform? I want to take a look at this because I think this is interesting. Recall that A of Z is the Graef transform composed n times of the P polynomial. It has roots alpha I to the R. And in order to recover alpha I from alpha I to the R, we need that the alpha I to the R are single roots of the Graef transform polynomial. Let's consider an example. I've chosen an example where the prime is 41 and I've got 6 roots. So the input polynomial has these 6 roots. So the degree of the input polynomial is 6. And we're just going to ask what happens when we square those roots. The Graef transform squares the roots. And we're going to square them once, then twice, then 3 times. And in this example, what you see is that when we square the roots once, 2 of the roots collide. If we square the roots again, nothing changes. We still have 4 distinct roots, so we would be able to recover 4 of the alphas. But if we keep squaring, if we square the roots again, most of the roots now collide, and there's only 1 single root. Over here on the right, I have the values of the parameter S and the ranges within which it lies. And over here is a theoretical approximation for the percentage of single roots we'd expect to get for this value of S. And you can see that if S is big, we get more of the roots will be single roots. If S is small, we'll get fewer. So the smaller the value of S, the faster the algorithm will go, but we'll get fewer of the roots. So there's a trade-off here. I want to get a large portion of the roots, but the bigger that I choose S, the more expensive it gets. But there is a problem here. The problem is the following. What if my polynomial has roots plus or minus 1, plus or minus 2, and plus or minus 3? If I apply the Graef transform to those roots, they are all going to square to give multiple roots. So the method won't work in that case. And the solution is written down here below. The idea is to randomize the algorithm. So instead of computing the roots of P of Z, we're going to pick a random shift, tau, and shift the roots around. So that's how we solve this problem. That will shift or randomly shift the roots so that we expect to get this proportion of the roots approximately will be single. Now I have on this slide a gory slide with details of the algorithm. There's several main steps. There's the step where we pick the random shift and we compute the shift. That I learned can be done fast using 1 multiplication of size d. There's the main tangent Graef loop, which composes n times. It applies the Graef transform n times, and it's the perturbed transform. So each time costs 3 multiplications, so there's 3n multiplications there. Then after we've done that, we have to evaluate the A polynomial, its derivative, and the B polynomial at the S roots of unity. That can be sped up using the Bluestein transform. It can be done in, there's 3 evaluations, so 3 order M of S work. And then we can go through and identify which roots are single roots, and for each single root, apply the lemma to extract alpha, the root of the original polynomial, and adjust for the random shift. This doesn't give all the roots. This gives some of the roots, 75% of the roots. So how do you get the rest of the roots? The method multiplies, takes the product of the roots that you've got so far. It takes the input polynomial P here. It divides by the product of the roots you've got so far. R here is the remaining part of the polynomial that we don't know the roots of. And then we get the roots of R recursively. And in the recursion, we're going to use a different random shift, so it's going to terminate. I have a couple of comments down here at the bottom about the technical detail of the parameter s. If we choose s in this range, on average, we will get at least approximately e to the minus 1 over 2 percentage of the roots. That works out to be 61% of the roots. If we choose a bigger value for s, we will get a higher percentage of the roots. But one of the steps of the algorithm, this step right here, becomes more expensive. So there's a trade-off there. And down the bottom, I've simply added up the cost of the various components of the algorithm and come up with a more precise statement about the cost of the algorithm than I showed in the introduction. So that's the end of the talk. I wondered, after we had done the implementation, I mean, if you go back and you look at the table of data, in this little table, I went up to 10 million. It easily goes up to 100 million, which is pretty big. And I wondered whether it'd be possible to compute the roots of a polynomial of degree 1 billion. That's 10 to the 9th there. Is it possible to compute the roots of a polynomial of degree 1 billion? I don't think that's ever been done before. And one of the difficulties is that it's going to need a lot of space. If we use 64-bit integers to represent the coefficients because of the size of the prime, 64 bits is 8 bytes. It's degree 1 billion. We will need 8 gigabytes just to store the input polynomial. We will need another 8 gigabytes for storing the roots. That's quite a bit of space. So after trying to optimize the algorithm for space, I did succeed in actually computing the roots of a polynomial of degree 1 billion. It took just under 4,000 seconds, and I needed 121 gigabytes to do it. My machine has 128 gigabytes, so I was working to cram it in to make it work. If you're interested in this work, we have published a paper on it, and I just refer you to this paper for details. Thank you. There's some references here if you want to take a look. The details of the work I published in this paper, which is available on the HAL archive. Thank you.